So, as we mentioned before, we want to find the sharp threshold function for property of being connected. And for that, we have to show two things. For here, we have to show this too. So if P is smaller than your desired function, the threshold function, then we have to show that it almost always do not satisfy this condition of being connected. It's almost always disconnected. And for probability function bigger than the threshold, we have to show that it's almost always connected. We have to show this too. For the first one, how do we want to show is that so our target function is this. So here, what? This log is log base e. So let's just write log instead of ln. So how do you want to show that? You want to show that if Pn is smaller than this, we want to show that there exists isolated vertex. So this will be sufficient for us to show that, because if there is an isolated vertex, then this is surely not connected. So that's how we want to approach this first one. Okay, maybe for that, we first consider the property of having isolated vertex. So before considering about connectivity, we first consider out the existence of isolated vertex as our property. So what? So we want to show that if we have an isolated vertex, and if it's bigger than plus epsilon times log n over n, we want to show that there are no isolated vertex. So that's what we want to show. Okay, so for that, we want to collect some tools. So what tool do we want to use? Let's say your x is the number of isolated vertex in a graph GNP. So that's your random variable. And for this, we want to show that the probability of x being 0 and probability of x being 0 is what? There are no isolated vertex means that this goes to 1. Then we want to show that there exists an isolated vertex, this goes to 0. We want to show this. Okay, but from Markov inequality, so we show this Markov inequality, that the probability of this discrete random variable being bigger than t is most if. So if the expectation goes to 0, then the probability of x equals 0 goes to 0. Because if you take t equal 1, this is discrete random variable. So this shows that if this goes to 0, and this entire thing goes to 0, so if you flip it, the event that x is not at least n is same with x equals 0. So we can show this. So that will be enough for us to show this. However, for the second one, we need a new tool. How do we show this? How do we show that this is almost always 0? Sorry, the other way around. This is 1. Okay, yeah. Forgive me for what I just said. So, yeah, so if this goes to 0, then this at least 1 is at most 0, goes to 0. So it's completely 1, this goes to 1. So using this, yeah, so we can show this direction. Okay, but what if, how do we show this? For this, what? We want to show that the probability that x equals 0 is go to 0. That means we want to show that the x tends to be large. But even if your expectation, say, goes to infinity, this may not necessarily hold. You could have a probability of x equals 0 being, say, 50%, half. But the probability of x being, say, very large, say, n over 2 is half. Then the expectation goes to infinity, while this does not go to 0. So we need some tool to deal with this case. And what's the rule? What's the tool? So we want to call something called we want to use something called the moment. We say that the r's moment of a random variable x is the expectation of x to the r. So x to the r is another random variable. So x is a random variable which takes the value as a real number. So x to the r makes sense. And we define the variance and we write it as a var x of x is the quantity of expectation of x minus expectation square. And the standard deviation is the square root of the variance. Okay, so with this tool, what we can show is the following relation, which is called Chebyshev inequality. So what's this? So this shows that how concentrated your probability measures are around the expectation. So for example, if you flip a coin n times, then the expected number of heads is n over 2. And if you actually compute the probability of getting number of heads as between 0 and n over 2, and you will see something like this. It's symmetric, and then the probability of getting n over 2 is high, and then it keeps decrease. So the probability is quite concentrated around the expectation. And then as you go further, the probability of having that value is small. So this is one of such instant, one guarantee such thing. So the probability that your value is away from the expectation by t is at most the variance of x divided by t squared. So if variance is small, then this is 4. And technically, okay, so this holds even if your x is not discrete random variable. Anyway, because here this part holds as long as your x is non-negative random variable. If you go back to the proof of it, then you can check it. And here you can use this Markov inequality to this Chebyshev inequality. We apply this Markov to the random variable x minus expectation of x squared. And the value a t squared. And what do we have? The probability that this bigger than t squared is, and most what expectation of this divided by t squared, which is the variance of x divided by t squared. So this is exactly this. And of course, this is non-negative random variable, this holds. Okay, so from this, what we can show is the following lemma called second Moore method. That's what we wanted. So what we have is this random variable x. We know that probability that x equals 0 is at most expectation of x squared minus, so expectation of the random variable x squared. You consider x squared and then take the expectation. Then you subtract it from the expectation of x, which is number squared. And then divide it by the expectation of x squared. Thus, what you said is that the probability of x equals 0 goes to 0 if the expectation of x squared divided by expectation of x squared goes to 1. If this happens, then what? This is what? This number minus 1. So this is, you can write it this way. So this holds. So let's prove this. Then what's the expectation of x minus expectation of x entire thing squared? So this is the term we have in this Chebyshev inequality proof. And using the linearity of this you expanded x squared minus 2 expectation of x times x plus expectation of x squared. Maybe let's mu be the expectation of x, which is constant. This is real constant. Then what? This is expectation of x squared minus 2 mu x plus mu squared. Then what we know? By linearity of expectation, this is same with this. So this is constant, this is constant. Constant just comes out as constant. And by linearity, it's same as taking expectation of this minus the expectation of this. But the expectation of 2 mu x is, you can take out this 2 mu. This is constant. So here. But what we know, this mu and this are same. So this is 2 mu squared plus mu squared, which is same as, so subtracting mu squared, and which is same as expectation of x squared minus expectation squared. Okay. Now what we know? From Chebyshev, we know that the probability that x minus expectation of x is bigger than or equal to p is what? This is the variance here. We let t be the expectation of x. Then what do we know? Then probability of x equals 0 is at most the probability of x minus expectation of x is bigger than or equal to its expectation, then what? So replace it the other way. This is and most this expression as expected. So this proves this second mono method. Now, with this tool, now we are ready to prove this theorem, which identifies the threshold function for having no isolated vertex. Let's say P is the function satisfies this. So here log is the natural log. So if it's C of n, if the function goes to infinity, then this G and P almost always has no isolated vertices. And if this C of n goes to the negative infinity, then G and P almost always has an isolated vertex. So, in particular, this n over log n is a sharp threshold for mean degree at least one. So this minimum degree at least one is the monotone property, which is the opposite of having isolated vertex. Then this shows that this function, I mean here you have n minus 1, so technically, so this is the other way. Log n over n is a sharp threshold function. So here, I mean this n and n minus 1, writing n minus 1 in the bottom doesn't really make any changes due to the definition of the sharp threshold. So this we can show. So what we do? We consider random graph model, GMP. And for each vertex in this GMP, we let I sub b be a random variable which is 1 if b is an isolated vertex, and 0 otherwise. Then, but let x1 be the summation of ib, be the random variable counting isolated vertex. So this 1 is here because this is same as counting the components of size 1, which are exactly the random variable. That's why we write this as a subscript 1. Later, we will consider general x of k. Then what? We can compute this expectation. So for each vertex, we know that probability that the vertex is isolated. So it has n minus 1 possible edges. All of them have to be not chosen. Such a probability is 1 minus p to the n minus 1. And you have this. I mean, now it's just the computation. You have this. So, I mean, we just rewrite it. And we know that we can take the expander of this log and this using this Taylor series expansion, you can write this log function in this way. And that's what? That's, I mean, for k equal 1, you have this term. And then for the all other term, what they decrease because this p is getting smaller at its highest power. I mean, so p is smaller than 1, so this is essentially n times p square, it's times some constant, you can bound the remaining one. So this is what? We know that this is n times exponential of minus log n minus cn plus p of what? Log square n over n. This is negligible. This is smaller than 1. So essentially what you have is that this exponential of negative log n cancels out. You get almost exponential of e of cn. So by Markov, what happens? If the cn goes to the infinity, then this goes to 0. Then by Markov's inequality, probability that this is at least 1 is m mod e to the c, which goes to 0. If this c of n goes to infinity. So this shows that this shows one direction. So if this holds, it almost always has no isolated vertex. The number of isolated vertex go to, it's almost always 0. Now we show the other direction. Assume this Cn goes to negative infinity. So we want to use the second moment method. So for that, we want to compute this. What's this? This x1 is indicator random, summation of indicator random variable. So this is what? This is summation of indicator random variable square plus UMV C1 IU times IB. Okay, so let's write it this way. For all u, you say that p is not u, not different from u. So this actually, in this way, uiv and I sub u times I sub p and I sub v times I sub u both appear. So let's write it this way. So this is n times n minus 1 term. Okay, but what do we know? This is indicator random variable, so it's either 0 or 1. So it's square and then itself is same. So that the first term is just x. And second term is this. Then that's what? That's the summation of expectation of this in multiplication of these two. However, what do we know? This is, again, indicator random variable. This is 1 or 0. And then when does it become 1? You have u, you have b. This is 1 only if both of them are 1. That means this edge and then these edges are all not chosen. How many edges? n minus 2 here and then 1 here. And again, n minus 2. So altogether, there are 2n minus 3 edges. If those 2n minus 3 edges are all not chosen. So what? Probability that this is 1, which is same as the expectation of it, is what? n minus p to the 2n minus 3. So, what do we know? This is what we get. Then what? This is roughly, so what was this expectation is n times 1 minus p to the n minus 1. And this is what? Roughly 1 minus p times expectation square. And as p goes to 0, 0. This is roughly this. So what? What we know, the expectation of x1 square over expectation of x1 square is what? You write this and this part goes to 1. And what this one was this. So if you plug that in, no, sorry. Yeah, you have this plus 1. And we know that these and these from the above computation, this goes to the infinity. So this is 1 over this plus 1, and then this goes to infinity as c goes to the negative infinity. So what? This tends to 1. So from this second moment method, but this holds though. From second moment method, we conclude that the probability that there are no isolated vertex goes to 0. So this finishes the proof. Okay, so this identifies the sharp threshold function for the property of having minimum degree less 1 or having no isolated vertex. Now, we are ready to find the sharp threshold function for connectedness of this random graph. So the same function, p, log n over n, is a sharp threshold function for a binomial random graph GNP to be connected. So one thing is clear: if p is less than 1 minus epsilon times log n over n, or maybe we can just take log n minus cn over n when c goes to infinity, then the above proof shows that with almost always it has a isolated vertex, so it is not connected. So that part is clear. So we are left with one thing. So let p be the log n plus cn over n, where this cn goes to infinity, but let's say it goes to infinity arbitrarily slow. It's going to infinity very slow as we want. If we prove it for this function, then for a function which grows much faster, it's immediately implied from this result. Because this connectivity is a monotone property. So let x of k be the number of components with k vertices in this GNP. Then C and P is not connected immediately when there is k, and which aside and most k n over 2, and G contains a component of size k. So, okay, as we already have analyzed x of 1, so we focus on x of k with at least 2. So this, we already know the probability. So we focus on the other case. So what's the probability that the xk is bigger than 0? And we want to add them from k at least 2 to n over 2. So this is at most the expectation of xk. Right? That's obvious from the definition of this expectation. And from linearity of expectation, what? In order to compute this, you choose all possible sets of size k. And that specific set of size k forms a component when it only forms a component if we satisfy two properties. So there are no edges from S to S complement. And then there exists a tree, spanning tree in this S, covering all the vertices. So if these two property holds, then we get the component. That's what. So you consider all F from this K, and for this S, you consider all 3T inside of this S. Let's say K sub n that induced by S, K vertex 3. The spanning tree in K sub F. And then for that, all of this has to be, this K minus 1 edges in the tree has to be chosen to be included in the random graph. And the edges between are not chosen. And then that's K times n minus K edges pairs between. So this, and then by linearity of expectation, so simply you count the number of such a set F, you have it. And then what's the number of these trees? That's actually known. The number of spanning tree in K is complete graph on K vertex is this. So distinct in, this is a vertex labeled graph. So this we will prove it later in the next section when we are learning about spectral graph theory. So for now, let's just assume. And probably, you have learned this in the discrete math course, and it's the prerequisite of this. If you are already familiar, then great. Otherwise, we will talk about this later. And you have this. So now what? What we have to show is that we want to show that the probability of not connected is 0. So we want to show that this has to 0. For that, let's say let AK be this number. And then we want to show that this goes to 0. So we want to divide the cases where K is small and where K is large. Let's say where K is between 2 and 10, so it's smaller. Then what we have is this AK is at most. So this is what? E times n over K to the K. This is upper bounded by that. Then you have K to the K minus 2. So, and your P is what? Log n plus C. Let's just write C. This is C sub n, but let's just write it this way. K minus 1. And this is E to the minus P. So log n plus C over n times K times n minus K. And as K is at most 10, so we can simply write 10 here. Then what? This term and this is K to the K. So let's write it as E to the K, N to the K, K to the K. So you take this away and then take this away, then you get n e to the k log n plus c to the k minus 1. And this is what? It's e to the minus k log n plus c plus 10 log n plus c k over n. Okay, as k is small, so this part is almost negligible. So if we want to put all the negligible part in here. So this part, this goes to 0 as n goes to infinity. So this part is almost negligible. We have to collect them. So, e to the k1 minus c from here and this. And so this and this is what? N to the negative k. And then you have one n here, then here. So this is what? Log n plus c over n to the k minus 1. And then this k square, we just forget it. Then you get this upper bound. Okay, and then maybe c is going to 0 as c is going to infinity as slow as possible. So this c is going much slower than this is growing much slower than log. So we can just delete it and then observe this into this term. Okay, so this is one. And for bigger value, we can again do the computation. And here, instead of this, what do we know? We know that k is n minus n over 2. So here, if you write it, and minus k times n over 2 times the probability p, which is n over log n plus c, so you can delete this, and k times log n plus c over 2. Again, you have this is n to the k, and this is n to the k minus 1, so only one n remains, and then 2k remain, e to the k, and log n plus c to the k minus 1, and this is what? Half log n is square root of n over 1 to the k here, and then e to the negative kc over 2. So overall, you have 1n here, e to the 1 minus c over 2, and log n, and square root of n to the k. And then let's add little 1 here to observe the remaining. So this is the upper bound. Okay, so now we have upper bound. So what? From k2 to n over 2, if you add all of them, here, this is, as k gets large, it's decreased. When k is 1, what? It's simply like log n over n times some e to the 2 1 minus c. And the remaining term for k bigger is much smaller than that. So it's almost this. And then for the larger term, what? When k is bigger than 10, this is simply smaller than like n to the negative k over 2, 1, and then there are remaining one is small. So this is simply n to the 1 plus liter of 1 minus k over 2 is from 10 to n over 2. And overall it's like n to the liter of 1 minus 1. So this is like sales. So now we have this. So that now what's the probability that the GMP is connected? This is what? 1 minus probability that there are no isolated vertex, and then you subtract all this AI, and that's like 1 minus 0 of 1. So this is something that goes to 1. So this proves that this is indeed a sharp threshold function for this GNP to be connected. Okay, and yeah, more things are known actually. So for example, if we just take GNM, and there is specific number n where this becomes connected. Okay, let's not do in this way. So we consider this GNM in a sense that you have a graph G, and you choose one edge and random you add. And then among the non-chosen one, you choose another edge and you add an edge. Then this is a process. The graph evolve. And then it starts from empty set, and then it ends up with complete graph. Then there is a specific moment that it becomes connected. That moment, let's say that moment is M sub C. And also there is specific moment that where it becomes minimum degree, at least one, so no isolated vertex. Let's say that moment is M sub 0. Then you can even show that these two are exactly same with high probability. Almost always. So anyway, so we have shown find the threshold function, sharp threshold function for being connected as an example of studying this random graph. Okay, thank you for listening. I will talk about how one can use linear algebra to study graph in the next time. Okay, thank you for listening. I will see you next time then.